Assalamu alaikum, my dear students. How are you? I hope you will be fine and okay. Today's our lecture number 20. I'm sorry, last time I just skipped one number, but it doesn't matter. Okay, as far as the topic are concerned, so the topic are in the exact order. I'm pretty sure about it. So today's our lecture number 20, and uh, this includes the dark concurrent carrying coil, MRI, and galvanometer. For the MRI, I wrote DIY, do it yourself, because it is application and you are now in class second year. So this is very simple. You can only read it from the your textbook. So you read it and then I will ask questions from you. So that is very easy. There is no much great detail or great physics for it there inside, but it just use the magnetic resonance imaging technique. This is why I just want to give this to you as an home assignment. And then our next topic would be the galvanometer. So let us start with the name of Allah Almighty. The first topic is the torque on current carrying coil. Torque on current carrying coil. On carrying current carrying the torque on the current carrying coil. Now, that is the basic principle involved here is very simple. That is whenever a current carrying conductor, a current carrying, whenever a current carrying conductor or coil, uh, conductor or coil, better to write coil, is placed inside uniform magnetic field, inside uniform magnetic field, it experiences a couple, or torque, which magnitude I write as torque equals beta cos theta. I will explain this to you right now. So this is the basic working principle involved. The torque on current carrying coil can be best understood if we just consider the mechanism of this. It consists of powerful radial magnet, which you see here. What? That is the powerful, number one, a powerful radial magnet. Radial magnet. Magnetic field, yeah, powerful radial magnet. Why? Because this radial magnet, it is used to concentrate the magnetic field to the center, like this, as the entire magnetic field is concentrated in the center, as you see here. Okay, so this is a powerful radial magnet, the curve shaped magnet, as you see the faces of the curve shaped magnet. Then there is the a rectangular coil A, B, C, D, or P, Q, R, S. What? A rectangular coil P, Q, R, S. This is a rectangular coil, right? The P, Q, R, S. Okay. Now there is what there is the axle, or that is there is an armature. Armature is when armature is in the assembly of coil, right? And that is, yeah, a shaft on which the rectangular coil which you see here is mounted on that. Okay, so this is the this whole assembly of coil, right? And the support or the shaft on which the coil is mounted is known as the armature, right? It is then supplied by using the copper rings and the carbon brushes, right? It is and a power supply. Okay, we have what? And here we have a power supply, right? Here you see some potential differences provide. There is commutator, and there is the brushes, the carbon brushes. The carbon brushes pass the current from the source to the commutator, and the commutators are connected uh, to the coil, and the commutator are the copper split rings. These are what? These are nothing but just copper split rings. This the purpose of the commutator is to keep the coil rotating continuously in one direction, either clockwise or anti-clockwise. It is a clever way of sweeping the direction of the current on the sides of the coil after every half cycle, right? To keep it moving in one direction. So this is these are the parts of the mechanism on which we can create uh, torque or coil on a current carrying conductor inside the magnetic field. Now you just see that when the current is passed, let's say for example, the current enters into the coil through the carbon brush X and leaves it to the Y. So you see here, look, there is what the current when enters here, the on the side PQ, the current is flowing in this direction. Here you see, and it leaves in this way. Now you know that, look, there is force on current carrying conductor, right? If you remember in the previous topic where I just told to you the force on the current carrying conductor, this force is according to the Fleming left hand rule. Look, there are what? The sides of the coil. I just want to write the sides of the coil. For example, how many sides do we have? One, we have side two, we have side three, and we have side four, as you see. Look, now let's see that whether they are contributing to the force, whether they can create the force, and what will be the magnitude of that force. The sides here, the sides of the coil, and we want that whether it contributes to the force, and if yes, what, right? The force on the current carrying conductor inside uniform magnetic field. You will see here, look. Now, what is the first side? The side PQ. Yes, the side PQ contribute. There is contribution from the side PQ. The side PQ contribute. It's create. There will be a force on the side PQ. Why? Because if you just apply the Fleming left hand rule, the force on current carrying conductor, then you see here. Look, the direction of the magnetic field. The direction of the magnetic field is what? The direction of the magnetic field is in this direction, as you see. Look, you see, this is the direction of the magnetic field, right? And if you apply the Fleming left hand rule, then look, the what will be the direction of the current on this segment of the coil? You see, look here, as the current is going this way, so there will be what? There will be the force, and the force will be in the upward direction. Look, the direction of the current, the field, if you apply the Fleming left hand rule, This is the direction of the field, and here the on this side, on the PQ side, the force will be what? The force acting on the PQ side will be calculated as beta sine theta, right? So you see that, look, because all the three, look, here the field, and here is the this is the field, and we have the current, and here we have, for example, the force, all are at right angle to each other. Since the current and since the current and that is the length, the current and the field, they makes an angle of 90 degree with each other. Therefore sine of 90 degrees in fact 1. So we have the force maximum here, and this force will be F, magnetic force, and it will be B now, where B is the strength of the magnetic field, right? And I is the current that pass through the coil, current I. The current I, and N is the number of turns in the coil. Here we have only a single turn, and A is the area of the coil inside the magnetic field. So this side contribute. Now let us see the side QR, that whether the side, any contribution from the side QR. Let's see to the side QR. As you see, the side QR, look this side, the side QR, it is parallel to the magnetic field. And if you remember the very first lecture, I told you there that if the magnetic field and the direction of the current is the same, then there is no force acting on it. So this side has no contribution, it does not contribute. Now let us see that whether the rest of the sides do the same. And here, yes, the RS side, there is contribution from the RS side, okay? And here the direction of the current is different from the direction of the PQ. So on the PQ, the pull is in the downward direction. Therefore on the RS side, the pull will be in the upward direction, and therefore there will be magnetic force of the same magnitude, but this will be in the opposite direction since it makes an angle of 90 degree at this position. Therefore the force acting on it will be maximum. Now let us see the SPQ side. Of course, it doesn't make any contribution because it is parallel to the field, so there is no contribution from them. So we have the two forces. If I label this force as F1, and if I label this force as F2, so you see here that F1 equals F2, right? The same in magnitude, but what? But opposite in direction. So now if you just see, look at the rectangular coil. This rectangular coil has the length of the rectangular coil. If you just see, look, this portion, this is the length of the rectangular coil, and this length is A, and B is the width of the coil. This is B. So definitely, and for the torque, this, since this is the axis of rotation, so this part is B by 2, and then the rest will, the lower part, that will also become B by 2. So if you just see, look, in this shape, or in this, let me make it in one bit good, like this. As you see, look here. So if this is, this will be what? This portion will be B by 2 moment arm, and this is another moment arm. So what we can say, that this whole B is in fact a couple arm. So there are two equal and opposite forces which acts on the at two different point of the same coil. Therefore it constitute what? It constitute a couple or torque. In this couple our torque is equal to what? By the definition of torque, torque is equal to what? It is equal to F into, that is what I'll be writing. I'll be writing here as the couple, that is the force into couple arm, right? This is what, because it constitute couple, so I will write couple instead of writing torque. Couple force into the couple arm, right? Now you just see what is this couple uh, force. You see that it is just equal to F, right, into the couple arm. Now this couple arm, this is a bit difficult to find, right? Now how we can find this couple arm? The force here right now is the equal to, that is the, I just already wrote this in advance, that better I should use the force as bell. Okay, bell, like the length of the coil. I just wrote it directly in the beginning, the formula, and I think I should change. You remember the force on the current carrying conductor? It was what? It was simply F, that is bell. F was equal to bell, and here that if I write F as bell, then here what is the length? The length we actually denoted by what? The length of the segment of the coil we have denoted by A. So I'll be writing BIA, so that I should not use a direct formula. I'm sorry for that. So this is what? This is the BIA. So we have the force here. Remember, the small a is the length of the parallel sides of the rectangular coil, length of the coil. Okay. So don't confuse it, is not area. So what I'll be writing here, that it will be equal to B I A. Now the couple arm. In this topic, this is the most difficult part, calculating the couple arm. Why? Because you know that once when the coil turns or it starts rotating, then there will be a point or case that force will be no longer perpendicular to the movement arm. And for maximum torque, for max, we have what? Force perpendicular to the movement arm, which is not the case here once the coil starts rotating. But that is not a difficult job. Here you see that, look, we have what? Here we have the magnetic field B, and you know on the side which has length what? Which has length A, right? And this is what? This is, look, this is B by 2, and look, this is also what? This is also B by 2, right? So you know that here what is going to happen, that we need the component of the movement arm which is perpendicular to force, because now when once it starts turning, then the force is no longer perpendicular to the movement arm and it does not create the maximum torque. So for this reason, we need the component of the force which is perpendicular to the movement arm, or the part of the movement arm which is perpendicular to the force. Clear? So for this reason, what actually we can do is, as you see, look, we have this as the movement arm B by 2. There you see. Here we have this as this is the B. I may write it like this. This is the B. Okay. And if you just see here, that is, if I just draw this end or this side, then you see that the force is what? The force is actually in which direction? The force is in that direction, right? So I need the component of this B which is perpendicular to what? Which is perpendicular to force. So in fact, I need what? I need that part of the for the that part of what? I need that part of the that part of the that part of the force. Okay, so that comes out to be what? That comes out to be, if this is angle theta, right? This is what? If this is theta and this is B by 2, so definitely it will be what? It will be the component of the force which is perpendicular to, which is perpendicular to what? Which is perpendicular to this force, right? This force. we need that, and it is indeed this component of the movement arm. As you see, look, I will label it with a green. So if this is b by 2, then this component, as you see, this component is perpendicular to the force, this component of the movement arm, if this is movement arm. So if this is angle theta, then this is definitely b by 2 cos theta, the easiest way, right? That is the component of the force, which is what, which is perpendicular to the component of the movement arm, which is perpendicular to the force. So what I will write here, that I will write it that it will be equal to the couple arm, but we need a couple arm. So the couple arm is this entire, from PS is the entire couple arm. So what I'll be writing, that b by 2 cos theta plus b by 2 cos theta. This is the couple arm. So it will be BIA into B cos theta, or BI BI BIA AB into cos theta. But you know that what is this AB? AB is the area of the coil cos theta. Since this is for one turn, so for n number of what, n number of turns, what we will be writing, A star equals B N B I A cos theta, or you can say bina cos theta, bina cos theta. So this is the torque on the current carrying conductor, right? Now let us move on to the next topic. Uh, the next topic is the galvanometer. Now, what is galvanometer? Galvanometer is, in fact, a very sensitive device which is used to detect and measure, to detect and measure a small value of a current or potential difference. Okay, so galvanometer is just does not detect the current alone, it can detect the potential difference also. It depends that how you connect in a circuit. If in series, then of course the current. If in parallel, then the potential difference. Usually the students thinks that galvanometer can only do for the current. Okay, so it does not. Now what is the working principle here? The working principle is the same, that the torque or the couple on current carrying coil, on carrying current carrying coil when placed inside uniform magnetic field, inside uniform magnetic field. So it work on the same principle. Let us see the structure. Here you see the galvanometer. It consists of powerful radial magnet, a rectangular coil A B C D, a rectangular coil A B C D, right? And then there you see the springs here, like this one, a hairspring, right? And the pointer you see, which is attached to the spring, and through the spring the potential difference is also supplied. The galvanometer can be connected, or voltage can be supplied to the galvanometer by using these terminal also. And if you just see, look the uh, view, in order to scale the galvanometer, here you see that there is what, there is the, for the scaling of the galvanometer, if we use the Lamb scale method, then we have here a mirror, right? We have here the what, we have here the suspension wire, the suspension wire, clear, and suspension wire, and we have the suspension wire, we have the suspension wire, clear. You see there we have the mirror, as you see, and the powerful radial magnet you already see, clear. Clear. So you just see there is the, for this reason you just see there is the spring here, and then look, there are two important thing here for the galvanometer. There are two kinds of couple. One we call the deflecting couple, the deflecting couple, clear. The deflecting couple is used to calculate what the, it is used to yeah, the deflecting couple is just because of what the torque or the couple acting on a conductor when placed in uniform magnetic field, and we have just done this thing right now, and that was Bina, if you remember, clear. So we have won this couple. The second couple is called the restoring couple or the torrential couple. The restoring couple, there will be acting what, the restoring couple. That is the restoring couple and the deflecting couple, they are completely acting in opposite direction to each other. One is clockwise and the other is what, anti-clockwise, so they opposes each other, clear. And once the restoring couple become, once the deflecting couple becomes equal to the restoring couple, then the pointer will stay at a particular point and indicate you certain reading, okay, which is when the galvanometer is scaled. So the restoring couple is equal to what? The restoring couple is equal to C theta, where theta is the angle of deflection. Angle of what? The angle of deflection. It is the angle at which the coil deflects, and this angle of deflection theta can be found by two ways, by length scale method, as I told you. Here how it can be found, look, just that is, you will note the initial position of the mirror, and once when the current pass through the galvanometer, then the coil will deflect, and then you will note the new position, and the reading must be noted on the translucent scale which will be in front of you. And this is how you can calculate the angle of deflection. Another way to calculate the angle of deflection is by using the pivoted coil galvanometer here. Okay, so these are the methods for which we can calculate this angle. This is the definitely it will have the dimension of what, and it will have the dimension of the torque, and it depends the restoring and the deflecting, and it depends on the geometry or the shape of the suspension wire. For example, the diameter of the suspension wire and the length of the suspension wire. So it depends on those factors, right? So once when the deflection torque equals to the restoring torque, then what will happen, that we have this as beta and we have this as c theta. Now what happens here is that I equals what, I equals c b n a into theta. Now we will, this whole is constant, I, this I equal into a constant, and this theta. Why? Because C depends on the geometry of the suspension wire. B is the strength of the magnetic field, which is constant. N is the number of turns in the coil, which is constant. A is the area of the coil, which is constant. then what happens here, that I is directly proportional to what, theta. This equation or the factor is known as the sensitivity of what, sensitivity of the galvanometer, the galvanometer. And the galvanometer will be highly sensitive. It will be what, it will be highly, it will be highly sensitive, highly sensitive, sensitive if it gives very large deflection, very large deflection for what, for very small value, for very small value of the current I, of what, of the current I. So the smaller the current and larger the deflection, then the galvanometer will be more sensitive. Then how this can be done? This can be done by C V N A into theta, right? So we can make this I that will be very small by either making this large, N large, or area of the coil large, or making this very small, C very small, small. Then we can make I small, right? So for small value, there will be what, a large deflection. Now let we explore various options. First of all, the stronger the magnetic field be, greater the strength of the magnetic field, then we can have what, we can have this I smaller. Yeah, for small value of current, actually better that this is what your book was saying, but better that I would write theta uh, B N A by C into I, like this. Then what I would write, that theta is directly proportional to I, like this one. So how I can make theta very large, not just discussing this I, but better to discuss these parameters. So either for small value of I or for large deflection, we can say like this. So if we make B very large, then what will happen? Deflection will be very large. And this is by using a very powerful magnet, or by increasing the area or the number of turns. So these are not the possible option, right? Not desirable, not desirable too much. Beyond certain extent, desirable, beyond certain extent, we cannot do this. Why? Because if you make the number of turns more, then what will happen? The galvan, that is the coil, will become too heavy and it may break the suspension wire. If you increase the area, then the galvanometer will become out of proportion, right? And it will be somewhat very bulky, right? And if you want to make the C small, then you may have to use a very thin wire. So a wire of a very thin diameter may cause trouble. It may break the wire, and this will not be a desirable option. So the only best option for increasing angle of deflection, or for small value of I, greater theta can be only obtained by making what? By making B very large, right? So this is the sensitivity of the galvanometer. So this was our today topic for the galvanometer, and I told you that we can measure this angle of deflection either using the length scale method or the pivoted galvanometer method, which will help us read the angle of deflection. Once the angle of deflection is known, then we can scale, or we can calibrate our galvanometer for the use ahead. Okay, so this is our today topic. Inshallah, see you in the next lecture.